When we finished up in the last unit, we were talking about the idea of antiderivatives, and it kind of meant the idea of undoing differentiation. However, we never really defined what good an antiderivative is or what good an integral is. So let's go ahead and get started by thinking about the idea of area. Now, a common shape that we're familiar with working with would be a rectangle. If we had a rectangle whose base went from 5 to 10 on the x-axis and had a height of, let's say, 4, we can pretty easily find the area of this rectangle using formulas that we're familiar with. The formula that we're familiar with for a rectangular shape is base times height. Now, when we look at this base times height for this particular rectangle, the base is a little more complicated. The height is pretty clear, it's 4. Well, the base goes from 5 to 10 units, so we know that that's 5 units, but if we want to think about how we could calculate that if it wasn't easy just to count, we would take 10 minus 5, the right endpoint minus the left endpoint. 10 minus 5 is 5, 5 times 4 is 20, so this would be 20 square units, because remember area is in terms of units squared. Now, finding this shape and the area, very simple. A couple things I want you to note about this. This rectangle that we've drawn is continuous, so this graph is continuous. So continuous meaning I don't have any jumps or gaps or holes in this graph, and it's greater than or equal to 0, so we could say it's positive or 0. So right here at this point, this would be the ordered pair 5, 0. So we have 0 here, but it's above the x-axis. That's kind of what we want to think. It's at or above the x-axis. And this is an important idea for this particular section. We're not going to deal with any functions or any graphs that fall below the x-axis. We want to get good at some other things first, and then we'll kind of look at those more complicated problems. So if we look at this as a horizontal axis, so if the horizontal axis is, let's say, velocity, and actually let's make the vertical axis velocity. If the vertical axis is velocity and the horizontal axis is time, what we have then is the distance traveled is the area under the graph of the velocity. So it's really neat how we can make that geometric connection. So again, distance traveled then would be 20, or the area underneath this curve for this distance traveled would be that area then. So let's go ahead and look at this in terms of integration. Now when we look at this in terms of this distance, it doesn't seem like that our units are going to come out quite right. Now area in general, we're talking about units squared here, but let's look at this problem. Vertical axis is velocity, so that would be something like 4 meters per second. Okay, and then the horizontal axis would be our time, and this would be, let's say, 5 seconds then. Well, if you notice, the seconds cancel, and I'm left with 20 meters here. So again, this is showing me my distance traveled. So it's kind of a neat little application of integration. But what if we have a geometric shape that I don't know the formula for? And that's the big idea here, where we're going to come up with one of the big pluses of integration. So, but what about an area? So a shape like this, except we don't know how to find a formula for that. But what about an area that is not a shape? That we can find the area of using a known formula. What do we do then? Well, that's where integration comes into play. Now there's a lot to this. We're going to learn some shortcut rules for integration, but before we do that, we need to get into the idea of summing rectangles, and that's what this whole entire section is about, is trying to come up with a good way to approximate area underneath a curve. One of the nice curves that I like to show for this, of course, has to be above the x-axis. and we go ahead and talk about the interval from A to B. And I want to find this area that's covered. So I'm trying to find this area. And we can see that it's definitely not a rectangle, and it's not a common shape that I know the area to. So let's make a few notes about this. The area under the graph means the area between the graph and the x-axis. Now this is only going to be true if we can assume, like we said above, the graph is continuous and positive. Now we can also be equal to 0 because it can touch the x-axis. But what we're not talking about is this area right here that would go on toward negative infinity, if you want to think about it like that. So we're only talking about this bounded area between the graph and the x-axis. Now we could estimate the area between A and B using a rectangle. Now there's two types of rectangles that we're going to be focusing on. Okay, let's go ahead and look at our first graph. Actually, I want to do an exact copy of this. Well, I'll do a pretty good curve sketch here. It'll be pretty close. So this could be 1. This could be the graph that I'm looking at from A to B. And this is the one I'll copy. So I'm going to have an exact replica of this. Now there's two types of rectangles that we're going to be looking at. One of the types that could be looked at is called inscribed. Now when I talk about an inscribed rectangle, that means the entire rectangle has to fit under the curve. And of course we want it to be as large as possible. We don't want some tiny rectangle down below. So this type of rectangle is called an inscribed rectangle. Now for this particular graph, this is an underestimate of the true area. So if I found the area of this rectangle, it would be smaller than the true area. Let's go ahead and look at our next rectangle. Now there's several different ways that a circumscribed rectangle can be drawn, but if we look at this graph, I can see that this is definitely going to be an overestimate, and this is called a circumscribed rectangle. And again, for this graph, it's an overestimate. Now some graphs, it could be an underestimate depending on whether it's increasing, decreasing in the ratio. So we don't always want to say inscribed is always under and circumscribed always over. You want to make sure that we take a look at the graph. So again, this is an overestimate of the true area. Now somewhere between the underestimate and the overestimate is the true area. So the true area is somewhere in between. So we drew one rectangle. So let's think about this. Let's kind of expand this idea. So if one rectangle is an estimate, might not be a very good estimate, but it's an estimate, would n equal 2 rectangles? N means our sample size here, so n equal 2 is the number of rectangles. So would n equal 2 rectangles be a better estimate? Now, one thing that we're going to do in this particular section, we're going to assume rectangles, our two rectangles that we're talking about. So assume rectangles of equal width. Okay, so when we're talking about that, we can just take another picture, same graph that we've had before. Hopefully it'll still paste out here. And let's go ahead and look at something really interesting that's going to happen. We could go ahead and try and draw two rectangles that might be a better estimate. Now, instead of writing circumscribed and inscribed, we want to talk about left and right endpoints, and then we'll also talk about midpoints as well. So for this particular picture, again, I want to use exactly the same width rectangle, so we're going to split right here. I would talk about our rectangle. Here's a rectangle and another one over here. I'm going to talk about these rectangles as left endpoints, meaning the height of this first rectangle, I'll go with the height on the left-hand side, not the right-hand side. So my next one, I would go where I could hit the graph, and this would be the height of my next rectangle. So these are left endpoints. Now, if we have left endpoints, you can imagine that we'll also have right endpoints. So again, I'm going to have equal width rectangles, so I'm going to split it right here. This would be my right endpoint, and then my right endpoint over here would be the height from here. So this is my right endpoint. So which is better, left endpoint or right endpoint? And the answer is it depends on the curve. And not only does it depend on the curve, it's going to depend on the number of rectangles that we have. So here's one rectangle, here's my other. I could find the area of each one and add them up, and you can see that for my left endpoint rectangle, it's a little bit high, but then my left endpoint over here is a little bit low, so they kind of cancel each other out, and this would be a pretty darn good estimate. Now over here on my right hand side, same thing. This right endpoint, which is an inscribed rectangle, is too low. It's too low of an estimate. This rectangle on this side, that's too high of an estimate, but the high that it overestimates and the low that this underestimates kind of cancels each other out, and it comes pretty close. Now there's one other type that we haven't talked about, and that has to do with the midpoint. So the midpoint, again, is going to occur right in the middle, because I want to split this into equal size rectangles. And so here's a rectangle. This is the midpoint of the first rectangle. This is the midpoint of the second. So I'm going to go up and hit the curve, and that is the height of my first rectangle. So you can see this rectangle does a pretty darn good job. It is underestimate here, overestimate here, but it's about the same, so they cancel each other out. Let's go ahead and do our second rectangle. I go up to the midpoint, hit the curve, and you can see on this one I have more of an underestimate than anything, but this is an example of midpoints. I find the rectangle, I find the middle of the rectangle, I go up and hit the curve, and that'll be the height of my rectangle. So a couple questions here. We looked at one rectangle and we saw it wasn't very good. Two didn't seem bad, but the question is then how many rectangles? How many rectangles would provide the best estimate? So, of course, if one was mediocre and two was better, three would be even better, and you can imagine what would be best is n, the number of rectangles, would approach infinity. So if we had an infinite number of rectangles, this would do a really good job estimating. And so guess what we're getting at? We're getting at the idea of a limit. So this idea of a limit is going to come into play here. So again, n is the number of rectangles, so an infinite number of rectangles would be the best estimate. but it's hard to draw an infinite number of rectangles, and it would take a long time. So we have to come up with some formulas to help us kind of deal with this, and it's going to be the idea of a limit that helps us out here. So let's go ahead and start developing some formulas. And I don't get too hung up on the formulas for these. I kind of like just to look at the problem and then start writing some formulas for area, base times height of a rectangle, and then summing them up from there. But if you want to go by formulas, I'll definitely put those down as well if you're more comfortable with that. So let's go ahead and look at the process. Let's go ahead and start for right endpoint approximation. Okay, so we're going to look at a little bit different curve, to kind of make it a little bit bigger, longer, so we can write a few more notes on it. But I want to talk about the process first. So basically we divide the interval a to b, and this is a closed interval. That's why we have our brackets here. Divide the interval a to b into n. Now remember, n is the number of rectangles, and I'm going to use a cap n here to be consistent with the formula. So into n subintervals of equal width. Now this idea of equal width is important. We will get into non-equal width in another section, but we're going to start with equal width. The width of each interval then would be given by the formula. We're going to call this delta x, and I'll tell you what delta x means here in a minute, is the width of the interval, which is b minus a, all over the number of intervals, which is cap n. Now delta x means change in x. So that's the change in the horizontal axis. So let's go ahead and put a nice graph up here, and then we'll start to try and kind of split this out. Now again, we're going to look at some problems, and in these problems that we'll look at, this will make a lot more sense when we put numbers to it, but we need to use variables to get started with the process of writing out our formulas here. So here's our curve, and let's say we're going from A to some endpoint B. Now I'm not going to really focus too much on where B is going to end up. We'll talk about that in a second. But it's somewhere over here. I want to look up my widths first. So each rectangle has a base or a width of delta x. That's going to be important. Okay, so let's go ahead and start writing out our rectangles. So for this example, let's go ahead and use 7 rectangles. And I could choose any number I wanted. I could use 7 or 10 or 100, but just for this example, I want to use 7 rectangles. So I'm going to go from A to B, and I might have to move this B. It'll kind of just depend on my scale of my delta x here. So I'm going from A to B, and I want 7 rectangles for this example. N equals 7 rectangles. Now, I don't want to get too hung up on the A and the B, what those particular values are, but what I know is if I start, trying to estimate this pretty close, if I start at A and each one has a width of delta x, this next endpoint is A plus delta x. And then I have that delta x again. Then this next endpoint is going to be A plus 2 of these delta x's. Because again, that width right here is delta x, and these are all the same widths. So this is A plus 2 delta x. And this will keep going until we get up to our 7th rectangle. So I have 1, 2, 3, 4, 5, 6. That wasn't off too far. So as we go and fill these out, again, each one of these has a width of delta x. Each one has a width of delta x. So you can see I'm just summing up how many delta x's that we have here. So this would be a plus 2 delta x. Here I'd have a plus 3 delta x, a plus 4 delta x, a plus 5 delta x. You get the idea. A plus 6 delta x. And then this point B basically ends up a plus 7 delta x. Now, where did this idea of our right endpoint rectangles come from? I have the bases. Now let's find those heights. Now remember, we're using right endpoint. So if I look at this first rectangle, if I look at the left-hand side, that would be a left endpoint, but I want to go right endpoint. So there's the height of my first rectangle. Here's the height of my second, third, fourth, fifth, sixth, and my last rectangle. So you can see sometimes right endpoint underestimates and overestimates depending on whether the curve is increasing or decreasing. So the height of this first rectangle is right here. This is f of a plus delta x. That's the height. Okay, so this is f of a plus delta x. Now it's going to be hard to draw the rest of these in. This one would be the height of a plus 2 delta x. So that comes across here. It's f of a plus 2 delta x. You kind of get the idea. They're going to be hard to squeeze in here because there's not this huge change in slope. Then we can also say as we start moving up again, they kind of start to overlap a little bit. So if I had to write out the formula for the areas of all of these rectangles, I just need to remember I'm looking at the base times height for each one. So my area is equal to r sub n. R stands for right rectangles. N stands for the number of rectangles. So for my first one, you can see that the base is delta x. So the base times the height. And in this particular case, that is f of a plus delta x. So that's the first rectangle. Second rectangle, delta x times f of a plus 2 delta x. Okay, and that comes from right here. Now you can see that these are going to get a little bit tedious. I shouldn't have done 7 rectangles because I'm going to have to write all these out. So this would be the base times the height, a plus 3 delta x, plus delta x, f of a plus 4 delta x, delta x times f of a plus 5 delta x, plus delta x times f of a plus 4 delta x. And remember, what I'm looking at is base times height. And I'll finish this and then I'll write that in. 5, this was 6, it kind of looks like a 4. F of x times delta x. So I have delta x f of a plus 7 delta x. So what I'm looking at for each of these is this is the base times the height of rectangle 1. This is the base times the height of rectangle 2. Okay? Now there's a shorthand notation for this, so that's what we want to look at next. So this would be equal to A equals, in this case, R sub 7. We know the number of rectangles, so let's put in that 7. If you notice, there's a delta x for every single one of these. So I'm going to go ahead and pull that delta x out front because it's common. And then what you can see that we have here is f of a plus delta x plus f of a plus 2 delta x plus f of a plus 3 delta x all the way up to f of a plus 7 delta x. Okay, the dot 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 means filling in the 4, 5, and 6. Well, this is a lot to write. What if we had 100 rectangles? So what we want to do is we want to shorthand this using summation notation. So for the nth case, for the Rn case, we can kind of write a shortcut formula that says, okay, well, let's go ahead and rewrite this. For the general case, R sub n, there's a delta x out front, so that again, that's the base. And then I'm going to use the summation notation. J equal 1 to cap n is the number of rectangles, of f of a plus, and if you notice it starts at 1, 2, 3, 4, 5, 6, 7, in this particular case, j delta x. Now what the summation notation is getting after, it means to change this indice. So I plug in a 1, I put a plus sign, and then I plug in a 2, put in a plus sign, plug in a 3, etc. So this is summation notation. We'll be working with this a little bit more. But this is the general formula that we could look at for right endpoint rectangles and summing them. Now the reason we want a shorthand notation is, what if we had 100 rectangles? We wouldn't want to write all these out. So we want a formula that helps us out with this. Now this will make a lot more sense when we look at a specific example. Now if you can do the curve sketch for any of these, you should, because it's going to be really a nice visual to help you figure out what's going on. So for this example, let's go ahead and calculate. Let's do R4, so that means right endpoint for rectangles, for the function f of x equal x squared, so that's a nice little graph, and let's do this from 1 to 3. Okay, so let's go ahead and look at a quick curve sketch. So we can go to our graphing calculator, y equal x squared, and you might have to adjust your window to make it look like mine. My settings are x min and x max -5 to 5, y min, y max going from -5 to 10. Well, the reason I went up 10 units is I know when I plug in a 3, I'll go at 3 squared equals 9. So if we go ahead and plug in this graph, we can see that we're looking at a parabola opening up with its vertex at the origin, but I'm only interested in this from 1 to 3. So I'm trying to find this area, and as it turns out, you can use your calculator to help you find this area exactly, but we're going to be using an approximation. So I'll show you how to find this exactly in a little bit later lesson. It's under your second calc option, and you can shade in that area and find it. So anyway, here's our graph. I'm just going to blow up kind of the part of my graph that is of interest to me, and that's definitely the part from 1 to 3. I want to make this pretty steep. So we'll say here's 1, here's 2, and here's 3. So I'm interested in finding this area. Now I need to use 4 rectangles. So right now it looks like I have 2 pretty natural rectangles already built in, but I want to have these equal width. So let's go ahead and split these in half as well. So now you can see that I have 1, 2, 3, 4 rectangles. Now I'm going to use right endpoint. So I'll go to my right hand of each rectangle, and that will give me my height of the rectangle. This one's an overestimate. My next one is an overestimate. Gosh, they're all overestimates. So I think that my answer is going to be higher than the actual area. But this kind of gives me an idea of a start. Now if these are all equal width, between 1 and 2 would be halfway, would be 1.5. Halfway between 2 and 3 would be 2.5. So when I want to find the area, I'm going to go ahead and use that formula that we had right up here. So let me copy it down again. R sub n equals delta x. And I'm going to sum j equal 1 to 4 because I have 4 rectangles here. And this is f of a plus j delta x. Okay, so get starting here, we have R4 equals delta x. Now remember, delta x is equal to b minus a over n, number of rectangles. So in our case, b minus a would be 3 minus 1, n is 4, so I get 2/4 or 1/2. So I have a 1/2 out front, and then I sum j equal 1 to 4. So I'm basically looking for the base times the height of each rectangle. I already have all the bases factored out front because they're all the same, and now I do the height. Now I have an a from this formula, that means I start at the number 1 plus j, and then delta x we already figured out was 1/2, so this would be 1/2 j in here. Now for this case it'd probably be easier just to brute force find the area of each rectangle and add them up. but I want you to make sure you know how to use the formula. So using the formula, I would have 1/2, and then I'd plug in j equal 1. So if I plug in j equal 1, that would be f of 1 plus 1/2 times j equal 1 would be 1/2 times 1 plus f of 1 plus 1/2 times 2 plus f of 1 plus 1/2 times 3 plus f of 1 plus 1/2 times 4. So if we write this out again, this is my base out front. Now this piece right here is 1 plus 1/2 would be f of 1.5 or 1.5. I think I'll think of this as 3/2, and this would be the same equivalent as 1.5 up here. Plus f of half of 2 is 1, 1 plus 1 is 2. 3/2 plus 1 would be 5/2, which is equivalent to 2.5, and half of 4 is 2, 2 plus 1 is 3. So all I'm doing is plugging in my right endpoints, 1.5, 2, 2.5, 3. And then I plug these into my original function, and which was f of x equal x squared. It's just up above. So I have a 1/2 out front, and again, if you wanted to, you could find the area of each rectangle. But this is going to be important that we know how to do this with the formulas, because eventually we're not going to use the number of rectangles. We're going to use n and then take a limit as n approaches infinity. So it's important that we be able to come up with this formula. So if I plug a 3/2 in, I will get a 9/4 back out. I guess I could show one more step here. 3/2 plugged in, squared, plus 2 squared, plus 5/2 squared, plus 3 squared. Okay, that would be 9/4 plus 4 plus 25/4 plus 9. And again, I have that 1/2 out front because that's the base of each rectangle. So I'll have 9 plus 4 is 13 plus 9/4 plus 25/4 would be 34/4. Or you could just plug this right into your calculator as well. 17/2, finding a common denominator so I can add those fractions, would be 34/2 plus 17/2 would leave me with 1/2 of 34 plus 17 would be 51/2. And of course 1/2 times 51/2 is 51/4. So I think I might have a mistake there. Let me double check something. Okay, if I look at my math, okay, I think it's right here. 13 common denominator, 13 over 1, multiply top and bottom. 13 times 2 is 26. Sorry about my bad mental math there. Then I'd have 26 plus 17. 26, 36, 43/2. And then of course when I multiply across I get 43/4. So this would be the area that's approximated using the right endpoint rectangles. So this is area using R4 on f of x equal x squared on the interval from 1 to 3. So this is my approximation of area. So it'd be about 10 3/4 units. I don't really care about the mixed numbers. I'm going to stay with my improper fraction. So that's a right endpoint. And again, when we looked at the picture, remember these are all too high. So this is an overestimate. So I guess we could note that. Just from looking at the picture, we can see that it's an overestimate. Now this particular picture, that's on a function that's increasing. So the right endpoint is an overestimate, but if the function had been decreasing, it could have been an underestimate. So we can't always associate a right endpoint with an overestimate. Now, let's go ahead and do the same process for left endpoint. These are fun. So this is the process for left endpoint approximations. So let's go ahead and use the same graph. I'm going to go up and grab it. Now there's some parts of this that we'll reuse and some we'll throw out. But let's go ahead and look at this graph. In fact, I think we can reuse a lot of this. So I'm going to grab a little bit more. Okay, so left endpoint approximation. So let me note first of all that this is left endpoint. We're just reusing a lot of our work because we can see that it's actually the same. We're still going to divide the interval into n subintervals of equal width. The formula for the delta x, the equal width, is b minus a over n. I'm going to use 7 rectangles here. The base doesn't change at all. It's the same process for the base. What changes is the height of the rectangles. So let me get rid of these old right endpoint heights and let's look at the left endpoint heights. Now some of these points will be the same because the right endpoint of one rectangle is the left endpoint of the other. What changes are the ends, either the rectangle on the far right or the far left. Okay, so I've got my graph back here. So if we're going to be looking at left endpoints, if I look at this first rectangle and I look at the left-hand side, there's my height. Notice, underestimate. Okay, this is my next rectangle, the left endpoint, slight overestimate. Okay, third rectangle, this is the left endpoint, overestimate. Overestimate. Very good estimate. Underestimate. Way underestimate. So you can see that some are a little higher, some are a little bit lower. Okay, so again, we have the same rules. The base of each rectangle is that same width, delta x. So when I start writing my generic formula for L sub n, I can think about this delta x being out front, because that's my base times my height. Now notice, though, this is a little bit different. This left endpoint, I'm starting right at delta x for my width, but my height I get when I plug a in. Remember, for my other one it was a plus j delta x. This one is going to be the same formula, but I'm not going to start my indice at j equal 1. I'm going to start at j equals 0. So I have my delta x, the height of my first rectangle, if I plug this in, would be f of a. So this is f of a. This is f of a plus delta x, etc. So this is f of a plus f of a plus delta x plus f of a plus 2 delta x plus f of a plus 3 delta x plus f of a plus 4 delta x plus f of a plus 5 delta x plus f of a plus 6 delta x. Now remember, the last one we went to 7. Let's see what we're going to do here. This last rectangle, I never get to a 7 delta x because I use this left endpoint, so I'm stopping here. But notice I still have 7 rectangles. 1, 2, 3, 4, 5, 6, 7. I'm just starting with that left endpoint. So if we had to shortcut this formula, L sub n equals delta x sum j equals 0 to number of rectangles minus 1 f of a plus j delta x. So it's really the exact same formula I used for right endpoint rectangles. The only thing that changes is my indice here. And the reason that it changes my indice is because I need to start with a 0 right here for 0 plus my delta x. So this is my formula for the left endpoint. Now let me see how I noted this before. I didn't make any particular note, R sub n. So now this is my formula for L sub n. Let's do the exact same problem we did before, except let's use L4 now in this one. So I'm going to do that x squared, f of x equals x squared. Okay, so I'm going to do the same formula, but now I'm going to do the same problem for L4. Now remember, one will be an underestimate, one will be an over, and then the true will be right in between the two somewhere. So let's go ahead and do an example. So for this example, let's go ahead and calculate L4, so this means left endpoint, for f of x, my function f of x equals x squared on 1 to 3. Now we already graphed this once on our calculators, but you could go back and do it again if you'd like. So let's go ahead and sketch in that graph. I'm going to make this pretty steep. So this is 1 to 3. Now I want equal width. I want 4 rectangles. So I want 4 rectangles of equal width. Now sometimes equal width is not the best case, but that's what we're starting with. We're going to do the best we can with that. So Ln equals delta x sum j equals 0 to n minus 1 f of a plus j delta x. And remember, delta x is equal to b minus a over n. Now I notice if we want 4 rectangles that 1, 2, 3, this is a midpoint right here would be 1.5 or 3 halves. And in fact, last one I used decimals. This is 5 halves. I'm going to put that in because we like to work with improper fractions. Actually, that's 3 halves. Here we have 5 halves. So I have these rectangles, but this time I'm going to use my left endpoints. So for this first rectangle, I'm going to start on the left to find my height. Left to find my height, left to find my height, left to find my height. Now notice for every single one of these are underestimates, and I can tell that from the graph. And we'll note that here in a second. So let's go ahead and go after our formula. B minus a over n, 3 minus 1 over 4, 2 fourths equals 1/2. So let's go ahead and look at L4. So my delta x would be that 1/2 f of, okay, so j equals 0. So I'm going to start with a, so this is going to be 1 plus 0, which is 1. Okay, my next endpoint, and I already know from the picture it's going to be 3 halves, but let's see how the formula works. So I'm going to go 1 plus 1 delta x. So 1 plus 1 delta x, and delta x is 1/2. F of 1 plus 2 delta x. F of 1 plus 3 delta x. Okay, so I have 1, 2, 3, 4 rectangles. Remember, f of x is equal to x squared. So this would be f of 1 plus f of 3 halves. And remember in our last one we used a decimal. F of 2 plus f of 3 halves plus 1 would be 5 halves. So I plug these back into my original. So this would be 1 squared plus 3 halves squared plus 2 squared plus 5 halves squared. This would be 1 plus 9 fourths. Some of these numbers are looking familiar, some of them not so much. So then I'll get L4 equals 1/2 times. Here we have 1 plus 4. I'll take the easy ones first, and then 25 plus 9 would be 34 fourths. Simplifying, I have 5 plus 17 halves. I'm going to find a common denominator so I can add these. So this would be 10 halves plus 17 halves. 27 halves. So when I get done, and I'm all said and done here, what I'm getting for L4 is 27 fourths for my solution. Now remember, way up here for R, if you can find it, that's L4. This was the area using R4, and it was an overestimate. this is our area. We're using L4. Still the same function, still the same interval. And when we look at this from our picture, we can see that each one of these rectangles is smaller than the actual area. So this is an underestimate. And we're getting this idea that it's an underestimate from the picture. Okay, so I'm kind of thinking that the true area is somewhere between the under and the overestimate. However, we have one other thing that we can do here. We can start talking about the midpoint. So we've already talked about the right endpoint, the left endpoint. We haven't really talked about the midpoint. So we're going to come up with a formula for the midpoint. So this is the process for, let's do midpoint approximation. Now, one was an under, one was an over. Midpoint might be our best bet, okay, but I think the best way to come up with that is to actually just look at our picture and then do our best estimate. So it's going to be the same setup. So let's see what I have here in my clipboard. Same process, except this time we're going to be using midpoints. So let me get rid of the stuff from our last example and then just change this picture to midpoints. Now when we change these to midpoints, my delta x's are the same. It's still a width of a delta x, but what's going to change here is where those delta x's are located. So I still have my a plus delta x here, but instead of using the right or the left endpoint of this rectangle, I'm going to use the middle. I'm going to hit the middle of each one of these. So each one still has a width of delta x. And then I'm going to go straight up, hit my curve, and that'll be the height of that rectangle. And if you notice for this one, it's both an under and an over. They almost cancel each other out. I'm going to go up and hit here. A little bit of an under, a little bit of an over. Under, over. Same here, under, over. Under, over. That one's pretty close to exact. Just kind of depends on how steep the curve is. An under and an over. So you can see I still have the 7 rectangles, under and an over estimate. Okay, so midpoints is quite a bit different. A little bit more complicated, but a better estimate. So I guess it's probably worth the investment that way. Okay, so we have a right endpoint, a left endpoint, and a midpoint. And so let's see what we can come up with for a formula. So MN, so this is the midpoint estimate of n rectangles. Well, we can see that each rectangle still has a width of delta x. And now what we need to figure out, and this is a little bit more complicated, so I'll write a little more work for this. I need to find the height of the rectangle by plugging in this bit right here. I need to plug in this red asterisk. Okay, so that was f of what? Well, it looks like to me it was a, so we're going to start at a, and then I just want to move up a half a delta x. Not a whole delta x, just a half delta x. Okay, so let's look at our next one. I'm going to start at that a again, but here's a half of a delta x. Here's another half, and here's another half, so that would be a 3/2 delta x. And you'll get the trend here pretty quick. A plus 1/2, 3/2, we'd have 5/2 delta x. Okay, so let's go ahead and keep counting. 1, 3, 5, 7, 9, 11, 13. So this is going to go all the way up to f of a plus 13/2 delta x. So let's go ahead and count that. 1, 3, 5, 7, 9, 11, 13. So that's 7 rectangles. Now this is a bit tricky. This one's kind of tricky to rewrite this using summation notation. So let's go ahead and look at this one pretty carefully. So let's look at m sub n. And again, this is in summation notation. Delta x, we know delta x is b minus a over n. This one's going to start at j equal 1 to n. So this is similar to the right endpoint in terms of the indice. But this is where the tough part comes in, where what this function is going to be. Now notice I cannot plug in values of fractions here, so I need to think about how I'm going to get that fraction out of j. My first one is a half, so if I could just take my indice of 1 and subtract a half, I would get a half back out. So this is my coefficient, j minus 1/2 delta x. Okay, and that's my formula. So when I go to 2, 2 minus 1/2 is 3/2, and I get my next value, and I stop at n. So this is my next formula that I'd like to be able to use, is this idea of a midpoint. So I bet you know what we're going to do next. We are going to look at the same problem we did last time, f of x equals x squared, but I'm going to use 4 midpoint rectangles this time. So example, let's go ahead and calculate M4 on the interval f of x equals x squared on the interval from 1 to 3. Okay? Nice parabola opening up. I'm going to make it pretty steep, so it's the same picture we've always had. 1 to 3. Halfway in between we know is a 2. So now I have 2 rectangles. Here is 3/2. Here's 5/2. So now my midpoints are not 1 or 3/2, it's this value in between these. So I need to find these points. Under, over, hit the curve, under, over, hit the curve, under, over, hit the curve, under, over. So these are the areas that I want to find. So now I need to figure out, okay, what's halfway in between 1 and 3/2. So let's go ahead and start calculating what we have here for my delta x. So I need 4 midpoint rectangles. I'm going to be using my formula m sub 4 then. So I'm going to have delta x, j equal 1 to 4. J equal 1 to 4, f of a plus j minus 1/2 delta x. Okay, so these look a little bit ugly, but once we start putting numbers to them, it's not too bad. My delta x has not changed this whole time. It's 3 minus 1 over 4. 3 minus 1 is 2. 2/4 is the same as a half. Okay, so M4. Have that delta x out front, which is 1/2. Okay, so for my first one, my value of a is going to be 1, because I'm starting at 1, plus j is 1 for my first indice. 1 minus 1/2 is 1/2. Now notice my delta x is also 1/2. So this is telling me what this point is right here. 1/2 times 1/2 is 1/4. 1/4 plus 1 is 1 1/4, which is 5/4. So this is the point 5/4. And that totally makes sense because 1 is the same as 4/4, 3/2 is the same as 6/4. So halfway in between 4/4 and 6/4 is 5/4. So let's go ahead and keep up this process. Okay, so 6/4, this would be 8/4. Halfway in between would be 7/4. So 5, 7, 9/4. 10/4, 11/4. But let's see how this plays out with our function. So this would be 1 plus 1/2. Actually, this would be 2 minus 1/2, which is 3/2 times 1/2. Delta x is my 1/2. Plus f of 1 plus 3 minus 1/2 is 2.5, or 5/2 times 1/2. Plus f of 1 plus, what are we at? for my indice. 1, 2, 3. This would be 4 minus 1/2 would be 3.5 or 7/2 times 1/2. Okay, so following through, this would be f of 1/4 plus 1 is 5/4. F of 1 plus 3/4, yep. 1 plus 3/4 would be 7/4. 1 plus 5/4 would be 9/4. And our last one, 1 plus 7/4 would be 11/4. Okay, so we go ahead and plug in our f of, so this would be 5/4 squared, 7/4 squared, 9/4 squared, and 11/4 squared. Okay, so have a look. 25/16 plus 49/16 plus 81/16 plus 121/16. Okay, we're combining our 25 plus 49 plus 81 plus 121/16 is, let's have a look. So these would combine 130, 251, 6171, 276 over 16. So we could multiply this out, or we could start reducing. 2 goes into 276 138 times. So I'm left with 138 over 16, which would reduce to, it looks like they're both divisible by 2 for sure. So that would be 65, 69 over 8. So this is my midpoint. So M4 is equal to 69 over 8. This is my area using M4 on f of x from 1 to 3. Now, I can't say it's an over or an underestimate. If I look at this picture, I think it's doing a pretty good job. So it's by the picture, it looks like it's a close estimate. Okay, now let's summarize the results from all three methods. So we've been working at this a while. You might want to remember what we were even trying to do a while ago. So we're doing 3 methods. Now remember, our right-in point, if I remember correctly, we thought was an overestimate. So let's go ahead and start with L4, because we thought that was an underestimate. M4 we thought was very good, and in this case R4 is our overestimate. Now this is not always going to be the case. Sometimes R4 will be over here as an under, and L4 will be an over. Usually midpoint's the best one. So remember, L4 was 27/4. Now if we look at this as a decimal, this is 6.75, but again, we'll leave it in fractional form. I just want to compare these decimal wise. I'm going to look at 69 over 8, and I want to think about this as a fraction with a denominator of 4. So this is going to look a little bit strange, but this is 35.5 over 4. The reason I'm doing that is I can see with the same denominator, I can just kind of look at these numerators. And as a decimal, it's 8.625. Now R4, which is my overestimate, was 43/4, and a decimal equivalent of that is 10.75. So we can see that my guesses at the area range from 6.75 to 10.75, and the midpoint is somewhere kind of right in the middle. Now, if we were doing a land survey and talking about the price per square acre of land or something, and we needed to get a good estimate, 6.75, I wouldn't get as much money from the property. 10.75, I'd probably get sued if they found out that I sold them more property than I actually owned at the end. But this is a pretty good estimate. Now, I'm going to give you the actual answer. So the actual area is 8.6 repeating. So you can see M4 is very close with only 4 rectangles. So imagine how good we could do with, let's say, 5, 10, 15, or 20 rectangles. But 4 rectangles is a pretty good job. Now, even though 4 rectangles does a pretty good job, let's think about what if we had an infinite number of rectangles. So instead of 4 rectangles, let's think about the limit as n approaches infinity of Rn, which would actually be the exact same solution as the limit as n approaches infinity of Ln, which is the same as the limit as n approaches infinity of Mn. So right, left, and midpoint. And if I did this problem and I took these limits with n rectangles, I would get the actual area of 8.6 repeating. So those are the kind of things I want to start developing here. Now let's go ahead and look at a couple of things about summation notation. And we've already talked about some of these when we were working with the previous problems, but I just want to make sure you have a few notes just to clarify a few things. So if we had a problem, let's say like j equal 1 to n, well, let's do 1 to 4, let's be specific here, of j squared plus 1, what I would do is I would take 1 and plug it in for j, and I'd get 1 squared plus 1. And then the summation sign means to do a plus and go to the next indice. After 1 would be 2, so this would be 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. So this is how I would rewrite this. Now if you'd go through and calculate this, you'd come up with 34. Now another way that we can look at this same exact problem is I can distribute the summation across the addition or subtraction, but never with multiplication or division. So same problem, I could also look at j equal 1 to 4 of j squared plus j equal 1 to 4 of 1. So this would be 1 squared plus 2 squared plus 3 squared plus 4 squared. That would be this first piece. But what is this? There is no j here. So what this looks like is 1 plus 1 plus 1 plus 1. This indice doesn't change. It's a 1 every time. So if I'm adding these up, I get 16 plus 9, 25 plus 4 is 29 plus 30. So this is 30 plus 4, or 34. Okay, so again, you can separate that across addition or subtraction, but never multiplication and division. We also have some power sums, they're called. They're kind of some shortcut formulas. So one of the shortcut formulas I have is j equal 1 to n, and I'll use a cap n to be consistent with the formula here, is of j is n times n plus 1 all over 2. Another power formula is j equal 1 to n of j squared is equal to n. I need to be consistent here and use these cap n's. N times n plus 1 times 2n plus 1 all over 6. And I'll explain to you in a second what these power formulas are for. I guess if you want to impress your friends at parties, it'll help you add up numbers really fast. J cubed would be n squared times n plus 1 quantity squared all over 4. So these are some shortcut formulas that are going to be handy for you to know. And they're going to make things a lot easier for you when you're working some of these longer problems. So let's see what they actually mean. I'll just do one example for you. So let's say I wanted to add up the first 10 digits. So this would be the sum of the j's, j equal 1 to 10, the first 10 digits. So this would be 1 plus 2 plus 3 plus 4, all the way up to 10. Now there's some interesting things that happen when you add up these digits. Notice 1 plus 9 is 10. 2 plus 8 is 10. 3 plus 7 is 10. And we're really good at adding 10s. 4 plus 6 is 10, and of course I have 10 itself. Then I have this 5 left over. So I have 10, 20, 30, 40, 55. So the sum here is 55. Well, that wasn't too hard to do, but what if this was 100 or 1,000? So what this formula says, j equal 1 to 10 of j, again, this is n times n plus 1 over 2. N is 10, so this says take 10 times 10 plus 1 and divide it by 2. So that says to take 10 times 11 divided by 2. 110 over 2 is 55. So this is just a quick way of coming up with these without having to add them up. And this works the same with the squareds and the cubes. So why did we learn this? Well, we learned this so we could start taking the limits of some of those formulas that we were looking at before. So we just did the x squared problem 3 different ways, and we're going to do it one more way, one last time, so we can look at this limit notation. So computing area as the limit of approximations is what we're looking at. So computing area as the limit of approximations. Okay, so same problem, calculate the area under the curve of f of x equals x squared on the interval from 1 to 3. Okay, so I can graph this, but it's not going to do me a lot of good anymore. So this is what I'm looking at from 1 to 3. But I can't split this into so many rectangles because I'm using an n number of rectangles. So this one's not saying to use Rn or Ln or Mn. This is just saying calculate the area. So I can take the limit as n approaches infinity of my right endpoint rectangles, or my left, or my midpoint. And I've got to tell you that using the midpoint is a tough formula unless you're going to just calculate it brute force. Also, left endpoint, remember, uses j equals 0 as your start point. That's also tough, because notice all of these shortcut formulas up here start with my indice of j equal 1. So I want to use Rn here. So what I'm looking at is the limit as n approaches infinity of my Rn, my right endpoint. So if I'm going to write this out, this is going to look like the limit as n approaches infinity of delta x times the sum j equal 1 to n f of a plus j delta x. So what we want to do is start filling in what we know. We know our delta x in this case is going to be equal to 3, I'll write the general formula, b minus a over n. So that would be 3 minus 1 over n, which is 2 over n. Because I don't know how many rectangles I have. I have an infinite number. So as I start writing out this formula, my area is going to be looking at the limit as n approaches infinity. Okay, let's go ahead and plug this in now. Delta x, which is 2 over n. Okay, so I have 2 over n. And then with this summation notation, I don't want to write out every single rectangle. I can't. There's an infinite number of them. But let's look at what this looks like. This says to start with A. A in our case is 1 because it's my left endpoint. Okay, because this is from A to B. So this is going to look like 1 plus j delta x. Now delta x was 2 over n, if you'll recall. So it doesn't really look like I'm making much headway here to make this a doable problem, but it'll get better here once I start trying to plug this in to the original. Because remember, our original function was f of x equal x squared. So let's go ahead, I'm not going to drop any of my notations. Don't want to drop anything because I might forget what I'm up to here. This is equal to 2 over n. And you know what? I have to be careful here. I keep dropping these to lowercase. Our textbook uses uppercase when I learned how to do this. Those were happy years. I learned how to use lowercase n, so I need to remember to use cap n here. Same as up here, just for consistency. And I'm doing as cap n approaches infinity. And again, it's not a big deal. I just want to try and be consistent. So these are cap n's. And again, the only reason I'm changing these is because our textbook uses cap n instead of lowercase n for our notation. Okay, so then this will look like j equal 1 to n. Now I need to plug in this 1 plus j times 2 is 2j over n quantity squared. The squared comes because I'm plugging in right here. And now I need to start simplifying the heck out of this. We're going to get some good algebra practice here. So this is a limit as cap n approaches infinity of 2 over cap n. Don't drop your summation notation. J equal 1 to n. I'm going to find a common denominator here of n, so I'll multiply top and bottom by n plus 2j over n quantity squared. And area equals limit as cap n approaches infinity, 2 over n, j equal 1 to n of n plus 2j quantity squared. So that's going to be n squared plus 2jn plus 2jn is 4jn plus 4j squared, all over cap n squared. Now I can simplify this quite a bit. I can pull out anything that doesn't have anything to do with an indice. So the limit as n approaches infinity. I can pull this n squared out because it's not affected by the j. So if I pull that out, I get 2 over cap n cubed, and then I'm left with the sum, j equal 1 to n. And again, this is n squared plus 4jn plus 4j squared. So now you can kind of see where these shortcut formulas are going to come into play and help us out. Okay, we're going to continue to simplify. Now remember, in the example we did above, we could distribute the sum across addition or subtraction, but this 2 over n cubed goes with everything. So let's go ahead and look at this as a equal the limit as n approaches infinity. And I'm going to keep this 2 over n cubed out front. Big bracket. So this is going to be the sum, j equal 1 to n of n squared, plus, I'm going to pull the 4n out front, because again, it has nothing to do with an indice, plus 4 I'll pull out front, j equal 1 to n of j squared. Now you look at these are the formulas from right up above. So let's go ahead and keep summarizing and simplifying. Limit as n approaches infinity, 2 over n cubed, big bracket. So this says if I sum n squared n times, that would be n squared plus n squared plus n squared n times. So this ends up actually being n to the third. Okay, so again, I'm taking n squared and I'm summing it n times, so n squared times n is n cubed. Now over here I have this 4n, and then I have the formula for the sum of the j's. Now remember, the formula for the sum of the j's is right up here. It's n times n plus 1 over 2. So this is n times n plus 1 over 2 plus 4, and then I need the formula for the sum of the j squared, which is n times n plus 1 times 2n plus 1 all over 6. And then I can close my bracket. And again, that sum of the j squared came from right here. N times n plus 1 times 2n plus 1 over 6. Okay, so we still haven't taken a limit. I want to get this to a point where I can take a limit as soon as possible before any mistakes can occur. There's quite a bit of simplification. 2 goes into 4 twice, and 4 and 6 cancel to 2/3. So that's a little bit of a help. So here I have n cubed plus, so 2n times n is 2n squared. So here I'm going to have 2n squared times n is 2n cubed plus 2n squared. So this piece right here, 2n times n is 2n cubed. 2n times n times 1 is 2n squared. Now the next one doesn't simplify quite as nice, but basically I have a 2/3 n, and then I'm going to FOIL this out. So I have n times 2n is 2n squared, plus n plus 2n is 3n plus 1. Okay, so we're still not ready to take the limit yet. Limit as n approaches infinity, 3 over n cubed. Now, as soon as possible, we want to get this into a form of a single numerator over single denominator. So I can either use my shortcut rules of limits or I can use L'Hopital's, one of the two. So n cubed plus 2n cubed is 3n cubed plus 2n squared plus, okay, so let's see what we have here. I'm going to distribute the 2n, but I'm going to leave it over this denominator of a 3. So this is going to be plus 4n cubed. Oh, gotta get that cap n in there. Plus 6n squared plus 2n, and this is all over 3. Now, because I have this denominator of a 3, I'm going to come back in and multiply top and bottom by 3, top and bottom by 3 here. And I've almost got this to a spot where I can take a limit. Limit as n approaches infinity, 3 over n cubed. So this would be 3 times 3 is 9n cubed plus 6n squared plus 4n cubed plus 6n squared plus 2n. Now I have that same common denominator, so this is all over 3. I think I'm on my 12th page of notes. This is kind of a long problem. It's a fun one though. Okay, let's simplify one more step. A equals limit as n approaches infinity. Okay, so let's think about simplifying this a little bit if we can. As we're simplifying, I see that the 3's will cancel. Okay, so when I think about canceling out those 3's, wait, I'm going to look back here. This is a 3 here, but if you notice, I have a 2 over n cubed, and then when I rewrote it down here, I wrote a 3 for some reason, so let me fix that up. Glad I saw that before I canceled that. It would have messed up my whole problem. Okay, so let's go ahead and simplify. I have 2 over n cubed. I can't cancel those 3's. Combining like terms, I have n cubed plus 4n cubed is 13n cubed plus 12n squared plus 2n. This is all over 3. So area equals limit as n approaches infinity. Okay, so let's go ahead and run this through. The 2 through would be 26 n cubed plus 24 n squared plus 4n all over 3n cubed. Now this is in a form that I can work with because I can take the limit of this. Now if I wanted to go ahead and take that limit to begin with, this would be infinity over infinity, which is an indeterminate L'Hopital's, and I could apply L'Hopital's over and over again. I'd have to apply it 3 times. Or I can remember my shortcut rule. And I like the idea of my shortcut rule here. Remember, if the degree in the numerator equals the degree in the denominator, the limit is the ratio of the leading coefficients. So if I want to look at this area, then limit as n approaches infinity of 26n cubed plus 24n squared plus 4n all over 3n cubed. This is equal to 26 thirds, and I can't just say equals 26 thirds. I need to say why, because the degree in the numerator equals the degree in the denominator, and that's my solution. Now, 26 thirds, 8 times 3 is 24. So this is 8 2/3. This is 8.6 repeating, which is the exact answer. So if I were to use any other method, I will never get a closer answer than this. This is definitely the longest method, but this is an exact measure. This is not an estimate. So these are fun little problems to work with. You got to keep track of your algebra. Don't make any typos, and if you do, go back and try and catch them and find them before you get completely done with the problem. Now, those of you who know your shortcut for integration, you would just integrate this curve x squared from 1 to 3. You're going to get the same answer, but there's not going to be any credit involved unless you go through the process of summing the rectangles and using the concepts of a limit. So, very long lecture, but I wanted to make sure that you saw all 3 complete examples without any skipped steps, and then so you could also compare the results from the left, right, and the midpoint. So our big thing here, our big idea is I can use 4 rectangles or 8 rectangles, but the best number of rectangles to use is an infinite number of rectangles. And so in order to use an infinite number of rectangles, I'll end up really taking my limit as n approaches infinity. These are longer problems, so make sure you leave yourselves plenty of paper. Make sure you show all of your works and make sure those of you who know our next step to go into Riemann sums and the fundamental theorem of calculus, if you want to use that idea to check your answers, that's great, but you won't receive any credit for anything unless you go through the process as indicated. As usual, good luck, and if you have questions, let me know, and remember Pearson Connect is a great help as well.